Good morning, ladies and gentlemen. My research topic is the omnidirectional motion control method of quadruped robots based on 3D-CPG oscillator group. First, after millions of years of natural selection, animals on Earth have evolved a set of rhythmic movement methods that can adapt to the surface environment. And biologists have found that the rhythmic behaviors such as walking, running, and other movements are self-regulating behaviors produced by the lower nerve centers in the spinal cord. Without the participation of the cerebral cortex. Based on this, the concept of the central pattern generator is proposed, and it is also confirmed that the CPG is a neural network composed of multiple neurons coupled to each other. A series of neuronal models were proposed to apply to legged robots control. This neural model based control methods has a clear bionic significance, which is equivalent to a phase control negative feedback system, and output signal can maintain a stable phase relationship, thereby automatically generating a rhythmic giant. However, this method has many parameters. This turning process is complex, and there is a lack of a clear corresponding between the parameters and the output waveform. Okay. Another type of oscillator model based on the system of nonlinear differential equations simplifies the biometric characteristics of CPG and proposes the CPG is essentially an oscillator with a stable limit loop. The Hopf oscillator is a representative of such models. Outputs two signals and form a circular limit ring in a phase plane, where any point in the phase plane converges to the limit ring after a short transition time. Some scholars have used 4 oscillators to control the 2 joints of the robot's forelegs, which greatly reduce the complexity of the CPG network. But the method still has 2 drawbacks. The first is that a single oscillator can only control 2 active joints. The second is that because the oscillator outputs directly controls the joint angle, it is intuitive to build a closed loop control within the foot space. And since then, the IIT has proposed an oscillator model with an elliptical shape limit ring. And the shape of the limit ring has been modified to make it appear semi-elliptical so that the trajectory of the foot and can be directly planned with the limit ring equation. This method has a good application on the robot SYQ, but it still has a defect that the oscillator has only two outputs, which is not convenient for the robot's omnidirectional motion planning. And our research starts from the elliptical oscillator model, optimized and extends it and take it as the core algorithm of our motion control framework. Our research mainly focuses on the online motion planning program of electronically driven quadruped robots with the goal of omnidirectional motion control of quadruped robots with trot giant. And the robot's control system is constructed based on CPG, and a general quadruped robot position control framework is verified through the dynamic simulation and prototype equipments. The figure on the right shows the virtual prototype and physical prototype of the quadruped robot built for the research. In this figure shows the algorithm framework of the control system of the whole machine. The core is the oscillator group composed of two oscillators in a blue fillet box, and one oscillator group is used as the foot trajectory planner. The outputs of the four master oscillators are coupled to form a frame network to act as a giant planner. The purple rectangle box represents each submodule. And the next step is to model and solve the kinematics of the whole machine. And the leg structure of the prototype is equivalent to a three joint robotic arm. Therefore, the coordinate system of all motor joints from the root joint to the end of the foot can be established according to the principle of the standard DH method, so as to describe the kinematic characteristics of the leg. In addition, the floating base coordinates system is introduced in this research to make the foot trajectory planning independent of the body posture. As shown by the blue arrow, the origin of the floating base coordinate system coincides with the body centroid. The z-axis is always point to the horizontal plane, and the x-axis is always pointed to the direction of the robot's progress direction. In this way, a direct connection between the foot trajectory and the terrain is established, and it is convenient to design an online foot trajectory adjustment strategy. Since the strategy planning in the end space is used to control the movement of the robot, so it is necessary to solve the motion angle of each joint according to the reference trajectory of the foot as the position control input of the driven driving motor. Since the z-axis of the coordinate system 1, 2, 3 are parallel to each other, so it is determined by the Peripheral criterion that the inverse kinematics has an analytical solution, and the pulsing expression of each joint angle is obtained by using the homogeneous transformation matrix, and the inverse transformation method. Next, innovative parts of the research, the motion planning method is based on the 3D-CPG oscillator group, which can achieve all-round motion planning by planning the foot trajectory to control the yaw of the body. A steering program can be decoupled into two components. First, those moving forward along the x-axis of the floating base system, and those that rotate around the z-axis of the floating base system. Based on this idea, our research proposed and rotational giant, and the figure on the left shows the movement of the rotation giant when the body is yawned gamma in a giant period. The corresponding hip joint node moves the delta x in the x direction of the world coordinate system, and the delta y in the y direction. And the delta x and delta y are obtained through the geometric relationship and then transformed into the coordinate system of the foot trajectory through the coordinate system transformation, so as to realize the support leg trajectory of the rotation giant designed directly in the foot workspace. And in our study, the rotation giant is incorporated into the mathematical model of the oscillator. The concept of the 3D-CPG oscillator group is proposed, and two methods are explored to construct the oscillator group. The first is discretized oscillator coupling method, that the foot displacement that controls the rotation according to the support phase time, and then linearly coupled the y direction output to the x direction output of the semi-elliptical oscillator. The method enables the real-time generation of 3D trajectories at the foot and under the CPG oscillator net framework. The red curve in the middle shows the oscillator output in the simulation environment, and compared with the original semi-elliptical oscillator output, it can be seen that the limit loop extends to the 3D space and still maintains a good steady state output. Simulation videos shows that the coupling method can achieve low speed rotational motion. However, there is a disadvantage of slipping at the foot when rotating at high speed.
I'm sorry, well, I will need to ask you to wrap up, please, because your time has ended. Thank you.
Okay, okay. Okay, I'm sorry to use too much time.